This conference will now be recorded.
Very good morning, students. Today,
This conference will now be recorded.
very good morning, students. Today, we'll complete this electricity chapter. At least the underlying theory part by discussing potentiometer bridge or potentiometer simply. First of all, let me tell you what we have learned already regarding this measuring instrument. We have learned Wheatstone bridge, meter bridge. So in Wheatstone bridge, we have seen there were 4 resistors, and at the balance condition, we know the arms ratio of the arms. Like, see, I have this figure. So if you remember, this part is A, this is B, this is C, this junction is D. So this is P, this is Q, this is R, and this is standard. And at balance condition, P by Q is equal to R by S. So this is what we have already learned. So this is not with respect to the resistors and current given here. This is with respect to the simple Wheatstone bridge. Okay. So today, let us first learn the potentiometer. First of all, why do we need potentiometer? Actually, potentiometer is used somewhat to calculate the voltage or potential drop across any element, circuit element. But in addition to that, there are various applications of potentiometer. Like if you have two electrolyte or two cells you have, okay, electrolyte cell, and you want to know what is the EMF, okay, so EMF of each, you should actually require one cell which has a known internal resistance as well as known EMF, okay. And to calculate internal resistance of any cell, this potentiometer is being used. So what is the working principle? Any unknown potential difference balanced on potential difference which is uniformly distributed over the entire length of a potentiometer wire. Actually, potentiometer is nothing but a long wire. You can see that. This is, see, this is, suppose you have some length of wire, like, and then you just break into equal parts, some 3 or 4 parts maybe. So 1 2 3 4 5 6 here. So we'll just break into 6 parts. Okay, you take a long wire and break like that, 6 part, equal part. Okay, then what do you do? See, there will be some metal strips, aluminum strip, or anything, any metal strips. If you have, you connect these two ends, then these two ends, and then these two ends. Okay, so this is a potentiometer. So these are the plates actually conducting plates. And see the end terminals. So this end terminal is connected to a variable resistor. Then you have battery. Okay, so point A is here. So as you see in the figure, so this is the wire, and you must be having a jockey. Sorry, yeah, yes, there will be jockey. This is the jockey. Look, this is the jockey, which can just slide over this wire up to C. Okay, and this is not like 100 centimeter or 1 meter. It can be several meters of length. Okay, like some meter, it can be a some meter, not only 1 meter, it can be much more than that. Okay, according to requirement we can use potentiometer of different length of the potentiometer wire. Okay, generally this potentiometer wire, that should be obviously a conducting wire, isn't it? And you know what is that made of? So that made of alloys, manganese, constantan, and eureka. Potentiometer wire. Potentiometer wire is made of alloys, manganese, manganese, oh sorry, manganese, constantan, manganese, constantan, and eureka. Constantan, constantan, and eureka. Okay, so these three, this is actually alloy of that. Okay, alloy of that. Now what we are going to do here with potentiometer, we will be applying Kirchhoff's voltage law to do any kind of calculation or whatever. So here actually potentiometer, as I said, it can be used to compare two cells and then find out the EMF of the unknown battery, as well as you can find out the internal resistance of the cell. Okay, so as you see in this figure, you look, this is a battery power supply which can send power in a closed circuit condition, all the branches, through all the branches. Then this is variable resistance, this is key. Okay, and this G is galvanometer, and this arrow is actually a jockey. Okay, that is jockey. Jockey can slide over the wire from beginning A to C. Okay, now in this case what we are trying to do, finding EMF of an unknown. Finding EMF of unknown cell. So to do that, you look here, I need two cells. I need two cells. Okay, I need two cells. One is standard cell. Suppose C1, sorry, epsilon 1 is, or E1 is EMF of the battery. EMF of battery. Sorry, cell 1. Okay, and this is the standard value which we know. This is actually known. So this is known. Now I have another cell which has unknown EMF. We need to find out that. We need to find out what is epsilon 2 in very simple word. So we have to find out what is this. To do that, we have to make some assumptions here. See, the wire we have used here can be uniform, can be non-uniform. Okay, but I am just considering that in the potentiometer, whatever see, we will just apply Kirchhoff's law to find out that. Okay, see, actually we have to consider that the potential drop unit per unit length, potential drop per unit length, which is denoted by phi also. Okay, that is potential difference per unit length. Okay, or voltage drop per unit length phi. And since this potentiometer wire is a uniform one everywhere, if you calculate voltage per unit unit length, you'll get this phi value. Okay, that means it has a potential gradient over the length. Sorry, there is a constant potential per unit length. Okay, per unit length. Okay, so now what we have to do? See, I can actually make a loop, closed loop over here. See what I'll do actually in this exam, see, or this is experiment or demonstration, the standard voltage will be connected to the circuit. Okay, this also has to be. So I have two cells, so where epsilon 2 is unknown. Okay, so these two other ends of the cells are connected to a three-way keys, and that goes to now up to the galvanometer, and galvanometer, like this, from this galvanometer to this actually. Okay, so if we apply Kirchhoff's law, then what is going to happen? But first of all, where we are going to apply this? See, first of all, let me connect A and 3 through this shifting keys, or this is triple key. Okay, so the first battery is connected to the COA key like this, so the circuit is complete now. Okay, now what I'll do, see, I'll just give a name. This is A, then this is suppose E, this is B, this is G, this is J. So, and then it will go all the way from then again A, E, B, G, and okay. So this is how a circuit gets completed. And if we apply the Kirchhoff's law, KVL here, let us say what let us see what is happening here. Applying so in this case, applying KVL for the loop A, E, B, G, J, J or N here. See J, let us say J. This is a complete loop. If I go again G, A like that, if I go. So if we work for this loop, then first, so let us see, when I connect this battery E, then the jockey connecting at N1 shows zero deflection for the galvanometer. So this is balance condition. So normally when you have so this cell and then this way I'm going, okay, A like that it goes. So I have to find out what are the, suppose this AN AN1, N1 is the point where the jockey finds the equilibrium, or sorry, unbalanced condition. So when it is this AN1, if this is suppose AN1 is length L1, if that is L1, so we can write down this U1 is equal to U1 is equal to, see, the total length into the voltage, this, sorry, voltage by length. So V by L into L. So this is actually the voltage drop, because galvanometer does not draw any voltage potential as a whole. Okay. So U1 we have got V by L into L1. Okay. And when the battery is connected, now the battery is shifted to this N2. When it is connected to N2, then suppose the null condition is found to be N2. So AN2, that is equal to the EMF of the battery itself. So E2 is equal to AN2. AN2 means AN2 is the length let us say that is L2. Okay, that is L2. L2 into 5. L2 into 5. And then this is actually okay, so L1 into 5, that is equal to the EMF. Okay, now so if we just do that, see E2 by U1, so E2 by E1 will get L2 by L1. L2 by L1. Okay, so if we compare two cells, see from here it is very easily we'll be able to get the EMF of the other one. Okay, suppose E1 is known. If E1 is known, then see E2 is equal to L2 by L1 into E1. So this is easily found out. Like you can easily find out that. Okay. So this is one way of using potentiometer. Then we can use, see here one point I think I have made you clear. Okay, so one point you need to understand that potentiometer wire has a constant potential gradient. Okay, so V by L, so this or potential difference per unit length, that is phi, that is constant for this wire everywhere. Okay, so this is the point we had to understand. Now we'll go to another use of potentiometer. So here I'll write how to use a potentiometer to find out internal resistance of a cell. See, this is second use of this potentiometer, and for that you know what need to do. You need to, see, instead of taking a known cell, you have to take a resistance box. This is resistance box, standard resistance box, where each key will insert certain resistance to the circuit if you open some resistors. Okay, some key from the bed, and this is the cell whose internal resistance small r has to be calculated. Okay, so look here, this is the potentiometer wire. As you know, see, jockey can just slide over the entire wire up to maybe the C, and this is battery arrangement, and this is like through which you can set a fixed current or you can vary the current also. Okay, all things are all right. This is G, means galvanometer. Now see, this battery, sorry, the cell is there. So now what we can do, we can actually apply Kirchhoff's law, KVL. KVL for So for this case, what we can do is, let us suppose initially this battery is closed. Okay, this is not okay. So battery is closed. First of all, this is closed. Okay, then no battery. So actually now I have not used any key or any battery of the box. Okay, at this condition, suppose the null condition is found to be E1, sorry, N1. Null condition is found to be N1. So look, here only source of potential is the cell. So we can write E is equal to phi into AN1. AN1 means it is L into phi. Okay, L into phi. Sorry, L1 into phi. L is the entire length, L1 is to phi. So this is so far good. Now when I initially this resistance box was open. Okay, initially the resistance box was open. Now the resistance box is closed and some resistance has been taken or connected to the circuit. Some resistance has been connected to the circuit. Okay, so in this case, what will happen, now this cell is actually also connected, never mind. So when this resistance box is connected and some resistance is plugged into the circuit, then see E AN2, this is L2, suppose this is AN2, null condition is obtained at AN2. AN2 means L2. Okay, this case it is when the resistor is connected, this is no longer EMF, that is voltage drop or voltage difference. Okay, so this is into pi. So this is the case. So we have got L2 into pi. L2 into phi. Now what we can do is, we can actually get E by V. What is E? If you remember, E minus I into small r is equal to V we have got. Okay. Either we can replace E by V. So E by V. So this is E minus IR. We know E minus IR is equal to V actually. Okay, that is V. And what else we have to do? and this is equal to I into small r. No, I'm sorry, just a minute. Okay, let us go to the next page. So E by V, V is equal to IR. Okay, this is E minus IR. Or E is equal to, see, E is equal to V plus R, IR, V plus IR. So this is the thing. And now look, E by V means E by V means, see, E is equal to phi into L1 and V is equal to phi into L2. This is what we have seen. So R plus, okay. We need to find out what is small resistance, okay, that is the internal resistance. So for that, what you need to do is L1 by L2 minus R by this minus of 1. This is 0. L1 by L2 minus 1. So this part we have got already. I think I have done just a small rearrangement mistake. So this is minus 1. This is R by, so small r, unknown resistance will be capital R into L1 minus L2. L1 minus, oh sorry, L1 sorry. So in this case, we need to see, so L1 by L2 minus 1. That is actually internal resistance of the circuit, of the cell. So this was actually brief of potentiometer uses of potentiometer. Here in summary, I will say that to measure the potential difference across the resistance, find out the EMF of a cell, and then it can, upon comparison, we can find out that, and it is found that internal resistance of a primary cell can be done. Okay, so now what we'll do, we'll see, we have seen that in case of, like with the help of potentiometer, we can measure potential difference across a resistance. We can measure the EMF of a cell. We can measure the internal resistance of a cell. Okay, these are the things we have learned. Now, voltage can be voltage can be measured by a voltmeter as well. But why do we need potentiometer instead of voltmeter? Because voltmeter has a finite resistance. Okay, voltmeter always has some finite resistance, but potentiometer doesn't have that. Okay, it does not draw any current. Potentiometer does not draw any current by itself. Okay, so now we'll go to the next section where we'll be discussing numerical problem here. See, this is not from the potentiometer, this is actually from the meter bridge problem. We'll just solve one by one, and we'll see how we apply the knowledge of potentiometer, meter bridge, and Wheatstone bridge to solve various problems. Okay, so first, this question is from Wheatstone bridge. Look, the current flowing through the resistance 2 ohm we have to find out. That means the current through this ohm, this. Okay, so here you look, this is a meter bridge, this is galvanometer, this is 10 ohm, this is 2 ohm, this is 25 ohm, this is 5 ohm. And what is, see, there is no battery here. Instead, how much current is entering at this junction A, that is given. See, if I compare this with the standard Wheatstone bridge, if you compare that, then what we are getting, see, this is A junction, this is C junction. You know the battery will be connected here between AC, between B, this is B and D. Between B and D, there is a galvanometer. Okay, and see the 4 arms of resistances are there. So this is named as P, this is Q, this is R, this is S. At balanced condition, you know, this will be P by Q is equal to R by S. So in balanced condition of the meter Wheatstone bridge, P by Q will be equal to R by S. Okay, we'll see whether the given bridge, Wheatstone bridge, is a balanced bridge or not. So at balanced condition, PQ by R, P by Q is equal to RS, that is what we have seen. So in this case, what is P? This is P. Let us say this is A, this is B, and this is D. This is C junction, and this is D junction. Okay. So in this case, if we compare the two resistances PQRS, then so what we get? P is what? In between A and D, A and B. Here P is 10 ohm. Q is how much? So Q is 2 ohm here. R is again 25 ohm. R is 25 ohm and S is 5 ohm standard resistance. Now see, you can see P by Q. P by Q you can find out. So P by Q ratio is 5 and R by S ratio is also 5. So if I take the ratio P by Q here, I get 5. P by Q is 5 and R by S is again 5. So we can say that this Wheatstone bridge is a balanced bridge. So balanced bridge means no current flowing through galvanometer. No current flowing through the galvanometer. Okay. So that means, see, the total current is actually getting branched into two. One goes all the way from A to B. Okay, so that means the total current, whatever it is given, 1.4 ampere. So that is divided into two branches, this and this. That means this is a so let us just do one thing, clean everything. Now we have found out that this is balanced bridge, fine. So there will be current this way. Suppose this current is I1 and this current is I2. Now look, these 2 points are at the same terminal of the battery. So what we can do? So this means I1 plus I2, this will be equal to 1.4 ampere. Okay. Now, since these two junctions are at the same potential, then I can write I1 into 12. Then that will be equal to 30 into 30 into I2. Oh, I2, yes. So 12 I1 plus minus 30 I2. This is one equation. Another equation is this one. We can put one value from here to here. Let us see. Let us say I2 is equal to so we can actually find out I1 here, 3 I2. So okay, this is one part. Then I have this equation as well. So this is I1 is equal to this. So we have to actually replace I1 or I2. I1 or I2 we have to replace. So I1 from here I2, let's say I2. I2 is actually 1.4 in minus 1. So this, if we put it here, I1 is equal to, okay, so we have already found out this. If we erase this part, let us see what is happening. So if I put this, I1 is equal to, or I2 is equal to, okay, so this is I1, I'm sorry, this is I1, okay. So look this point. One point four minus of I1, so 1.4 minus 5 by 2 into I2. So this I2 will go here. This will be 6 I2. So after this will be actually 7. 1 plus of this, so 7 by 2 into I2 is equal to 1.4. This will be, so this will be 0.4 ampere I2. Then what will be I1? I2 was 0.4, so it will be 1 ampere actually. So this is how we have to use Wilson bridge to solve various numerical problems. I think I'll stop it here for today. In the next class, we'll start with a new chapter. But later on, we'll come back to this topic again. to solve numerical problems in between. Okay, so thank you for your patience. Bye for today.